No, you can call it Gil. Oh, yeah, cool. Hello, hello. We're going to get started here. Take their seats. Also, there's some snacks, so feel free to go grab some snacks at any point in time. We know it's like kind of around some people's dinner time, so if you start feeling the rumble of the tumble, then please go grab some snacks. Feel free to do that. Awesome, sweet. Just let everyone settle down here. And everyone on, Julia, can I just get a thumbs up? We're all good on Zoom. Sweet, cool. I'm gonna try and stay close to the computer so you guys can hear me, but do tell me if there are any issues. Feel free to just unmute and just tell me that way. Cool. Alrighty. Well, everyone, thank you so much for coming to the High Power Rocket Club's project presentation night, also known as HPRC. Thank you so much for coming, and again, some food in the back. If the clicker responds, there we go. First, a little bit about tonight's agenda. We're going to start off with some brief introductions, and then we're also going to go into our Rocket Division's project presentation section. After that, we're going to have a little brief intermission for the bathroom, etc., and then we'll go straight into our Payload Division's presentation. Finally, we'll round it all out with some Q&A and some Zoom rooms where people can ask some questions, interact with the team, and maybe get some questions answered. Starting off, a little bit about the team overview. So we are a sub-club of the AIAA. We consist of 126 students of all different grades that come together to form two divisions, Rocket and Payload. We'll get more into those a little bit later. The two of those teams are responsible for different sections of the project. They have 7 sub-teams that make up the two divisions. We'll get more into what each of those are and what they mean a little bit later. We have 16 club officers and sub-team leads. These are the people that manage the logistics, the money, the safety of the team as a whole throughout the year. And they really make the gears turn as the team as a whole. A little bit about our team history. So we started in 2018, formerly known as the WPI USLI, or University Student Launch Initiative, which was a competition run by NASA, actually, out in Huntsville, Alabama. It had a 5,000 feet target altitude, and it consisted of about 44 student teams. Together, this competition really focused on the technical documentation writing and the design lifecycle, focusing on robotic payloads launched from rockets to solve various challenges each and every year. For this year, however, we are part of the Intercollegiate Rocketry and Rocket Engineering Competition, also known as IREC. It's the world's largest intercollegiate rocket competition happening in Spaceport, America, New Mexico. In the month of June, we'll be heading out there with our rocketry advisor, Curtis, and our faculty advisor for that trip, Professor Miller. And we'll be launching a rocket over the course of a week and also conversing with many of the other teams there. Teams from all over the world come to this competition. It makes up about 150 student teams, and it's really been an opportunity for us to grow as a team to a much larger scale as a team and push ourselves in our engineering challenges, really bend the possibilities of what we want to do as a team and try out new things. We were going to have a guest speaker, but they had a conflict for tonight, so we're moving on straight into the Rocketry Division presentation. Troy. Thank you very much. Go.
Okay, how's it going, everyone? Good evening. My name is Troy Otter, and I'm the Rocket Division Lead for WPI HPRC. As our name suggests, we are responsible for the design and construction of the rocket we will be flying. The Rocket Division is the larger of the two divisions, consisting of about 90 students split among 5 sub-teams. The mission of the IREC competition is to design and build a rocket that will launch a payload to an altitude of either 10,000 or 30,000 feet and then return to the ground safely. This year, we are participating in the 10K COTS category, which means we will be flying to 10,000 feet using a commercial off-the-shelf solid motor. We are scored based on overall technical prowess as for our rocket design and how close we get to our target apogee. I am excited to present the design of our 2022 competition rocket for the Spaceport America Cup. This year's vehicle has a diameter of 6 inches and stands at 11 1/4 feet tall. Fully loaded on the launch pad, the rocket is going to weigh 68 pounds, and with a motor producing 500 pounds of thrust, will reach a maximum velocity of over 600 miles an hour. This vehicle represents a significant step forward in our club's history, integrating multiple advanced new features, including a custom avionics system, a new air brake design, our first large-scale composite components, and a novel recovery system. Tonight, each of our sub-teams are going to take you through the various aspects of their designs, and we're going to begin with the aerostructure sub-team.
So aerostructures is responsible for the outer structure of the rocket. And on the picture at the bottom, you can see the different fiberglass sections of the airframe and the rocket. So at the top, we have the nose cone, the upper airframe, middle airframe, the electronics bay, lower airframe, and then at the very bottom, we have our two main components. So those are the fin can and the tail cone. So the fin can helps with stability and keeps the rocket straight during flight. And the fins also stay attached to the fin can so that they stay on during flight. And then the tail cone reduces drag on the bottom of the rocket and also attaches to the motor retention subassembly.
So the fin can ensures the fins are straight and thus the rocket is stable in flight. The fin can is also responsible for making sure the fins don't break upon landing. We made it by attaching 4 fins to the body with structural epoxy fillets and ensured its strength with 4 tip-to-tip fiberglass layups, stretching from one end of the fin to the next. We ended up choosing fiberglass layups and using a fin jig over fin slots because of its low weight and high strength. The fin can ensures the fins are straight and thus the rocket's stability in flight. The fin can is also responsible for making sure the fins don't move. Okay. Okay. So the tail cone reduces drag around the end of the rocket and holds the motor casing. We constructed it in 3 steps. First, the mold was 3D printed, which you can see in the bottom right, and the fiberglass sleeves were laid around the mold, which you can also see on the bottom right. So, and in the top right, you can see the final product and the bulkhead, which is used to attach to the motor casing. Similar to the fin can, we made it with strength and weight in mind. Using fiberglass afforded us the low weight, while laying around the mold gave us the strength we desired.
So to make sure our materials can withstand the forces they are facing during launch and landing, we ran a series of tests using ANSYS. So for the fin can, which you can see on the right, or sorry, the left, we did mostly transient structural analysis, which would be to simulate an impact force of the ground, specifically if the fin can were to say land on a rock. And for the tail cone, we did more static structural analysis, which would simulate more of a constant force during the landing. Also, in the next coming weeks, we plan on doing more physical tests of our composites to make sure that the expected results match our simulated results that we got using ANSYS. And next up, we have couplings.
Hello, everyone. The coupling subteam is responsible for rigidly connecting different sections of a rocket airframe together. This year, we decided to connect the fin can and lower airframe, the lower airframe with the electronics bay, and lastly, the electronics bay with the middle airframe. On the right, we have an animation of the couplings assembling and disassembling.
So a traditional rocket airframe joint is made up of a short coupler tube that extends into the airframe on either side of the joint and keeps the section stiff. The tube itself is held in place, the tube itself and any internal components are held in place with bolts going through the airframe. And the downside of this design is that it's difficult to manufacture and assemble, as lining up the small bolts can be a challenge. You also have to include features in your parts for these bolts to thread into, which can increase manufacturing complexity. Our new coupling design, as shown there, is stiffer, lighter, easier to assemble, and completely standardized across the airframe. The preload derived from our threaded connection helps cancel out the tensile stresses due to lateral loads, and with this, the resultant load on the airframe joints is only compressive. This means that the joints are not pulled apart during flight and the vehicle remains stiff. The couplings are also significantly lighter than a coupler tube and take up less space in the airframe. They also feature integrated mounting flanges, as shown, to make attaching components to them easier than to the coupling tube. And to verify that our couplings were strong enough, we performed a series of structural simulations in ANSYS to refine our design. And then once we had an actual physical prototype, we conducted a real-world flexural test at the worst-case flight loads. These tests allowed us to gain more confidence in the novel design and let us move forward with implementing it into the final rocket.
Our motor tension system was designed to transfer thrust from their motor to our airframe via thrust coupling and securely hold the motor casing inside the rocket throughout flight. We performed several static simulations on the buckling failure mode of our standoffs and yielding of our thrust coupling. Our team spent several weeks in the machine shop manufacturing 3 coupling joints and our motor retention system. Prior to this, we optimized machining processes by cutting threads on smaller test pieces to ensure we get high quality threads on our final product. We also designed several work holding fixtures to allow us to machine our parts more efficiently. With an overview of the couplings completed, we will now move on to our recovery system.
The recovery sub-team is responsible for the design of the parachute system used to return the rocket to the ground safely. The vehicle uses 2 parachutes, a drogue parachute deployed at apogee to stabilize the descent of the vehicle, and a main parachute deployed at 1,500 feet above ground, used to slow the vehicle down to a safe velocity for landing. Traditionally, high-power rockets store each of these parachutes in different sections of the vehicle, and the airframe separates in 2 or more locations using black powder charges to release them. This year, the recovery team took on 2 new challenges, the first being that the separation of the airframe is accomplished through the use of a CO2 system rather than the traditional black powder, reducing the need for energetics on the vehicle and the added bonus of reliability that CO2 provides at higher altitudes. Second, the vehicle has 1 separation point, reducing mechanical complexity and the space taken up by the recovery system. In order to perform these tasks desired for the system, the team had to create a more intricate line system than the traditional. At our first deployment at apogee, the CO2 system will separate the upper and middle airframes. The separation of these airframes pulls the drogue parachute out, while the main parachute is secured inside the middle airframe in a bag by a hair tie. At this point, the drogue parachute line pulls on the drogue unloader, which is attached to the vehicle through the redundant tender descenders. Tender descenders are a pyrotechnic release, and at the main deployment, each tender descender has a small black powder charge in it that ignites and separates the connected shock cord. This allows the drogue line to pull the main parachute out of the bag and unfurl to safely land the rocket.
The primary function of the recovery bay is to house the altimeters and the ejection system hardware. Other functions are to serve as an attachment point for our parachutes and to protect the recovery bay from ejection gases. The bulkhead plate is made from aluminum, so it can also withstand the forces of the parachutes pulling on the eyenet coming out the top. All of our electronics are mounted on what we call a sled. The sled is 3D printed from polycarbonate, so it can withstand the extreme temperatures the rocket faces on the launch pad and at apogee. We decided the shape of the sled should be a half hexagon so we can optimize the amount of surface area we have to mount electronics while still fitting the CO2 ejection system behind it. We have 2 ejection systems on the rocket. One consists of our primary altimeter and a CO2 ejection system, and the other is the backup altimeter with the same CO2 ejection system. The primary system fires at apogee and then at the second event at 1,500 feet, and the backup system will fire 2 seconds after to ensure the parachutes get out of the rocket. In the recovery bay, we were trying to fit everything in as little space as possible. We started making the recovery bay by creating a prototype so we could lay out all the electronics and CO2 ejection systems to make sure it all fits as intended and everything is accessible. From there, the team routed wires to make sure this layout was possible. After making the appropriate changes, we used a CNC mill to make the bulkhead plate, and the sled was 3D printed. Multiple copies of this plate are being made so team members can learn how to go from CAD to CAM and then machine a final product. The recovery system is one of the most critical systems on the rocket, so every aspect has to be tested so the rocket lands correctly. Our first test this year was a CO2 ejection test to determine what size CO2 canister is needed to separate the airframe from the nose cone. We tested several different sizes to determine this. Since this year we're keeping the main in a bag, we needed to see if the drogue has enough drag to pull the main out of the bag. We did this by doing 2 drop tests. One was tethered to a tree and the other was throwing a test stand off a parachute or off a parking garage to make sure the main parachute will come out of the bag. To verify our altimeters are working, we use a vacuum chamber to set the pressure to apogee and then main to make sure the altimeters fire their charges correctly. Lastly, this weekend we plan on flying our new single end deployment system in last year's rocket to make sure it works. And next we'll hear from the air brake sub-team.
The goal of the rocket this year is to reach a target apogee of 10,000 feet. To help us reach that goal, we have implemented a system of air brakes. The air brakes job is to deploy a set of fins that help increase the amount of drag that the rocket feels. And as a result, will slow down the rocket enough to help us reach the target apogee. In our initial design, we wanted to limit the amount of friction and binding that the air brakes would feel. So to help us, some initial designs that we looked into were a rack and pinion and even fins that would deploy by rotating in the outer airframe of the rocket. However, we ultimately decided to go with a linear rail system, as the linear rail system provided the most stability and was more consistent than the other models. In our final design with the linear rail system, we ended up having 3 main plates. The rail mount plate at the bottom provides most of the stability for the air brakes and also allows for the linear air brakes to be, or the linear rails to be attached. In the actuator plate, it attaches to the servo and allows for the fins to be deployed. And in the coupler mounting plate, it attaches the servo and also allows the air brakes to be attached to the lower airframe of the rocket. On each one of the fins, there's a press-fitted bearing that decreases the amount of friction and allows the fins to go smoothly while the air brakes are deploying. There's also a pillow mount block that is attached underneath the servo that limits the amount of side-to-side motion and also protects the servo from any damage.
Next step in our process was to verify our designs. To verify that the air brakes would be capable of effectively controlling the apogee of the vehicle, we began simulating a normal flight using OpenRocket, which is an open source software. From this trajectory, we selected a series of points that were representative of the full range excuse me, of the dynamic pressures the rocket would experience during flight. At each of these points, we used the SolidWorks FlowSim software to determine the drag on the vehicle at multiple air brake extensions. Using results from these simulations, we were then able to put this data into MATLAB to determine the relationship between dynamic pressure, air brake extension, and drag on the vehicle. At maximum velocity and full extension, the air brakes will produce a drag force of 23 pounds. With this data in mind, we then moved on to prototyping. The creation of the prototype was essential to confirming that our design would work the way we intended, and that the air brakes would properly deploy as they're critical to reaching that 10,000 foot apogee. From our prototype, we were able to verify that the linear rails would provide a reliable actuation with low friction and that we would be able to avoid binding. The prototype also proved to us that the fins were moving with each other at the same time. And this was important to reduce the risk of aerodynamic moments causing the trajectory of the rocket to fluctuate and destabilize. Lastly, this test proved that the air brakes were structurally sound and restricted any unintentional motion in the system. After having proved our air brakes design through prototyping, we moved on to manufacturing. During this last C term, our sub-team began manufacturing in the shops here at Washburn. Most of the components were machined in-house, made by our students here out of aluminum. Most of the operations were completed on CNC mills. That way we could ensure the parts were made accurately and within our tolerances, making them suitable for our purpose here. Thank you.
Awesome. Thank you. Sweet. So we're running a little bit ahead of schedule, of course, but I know it can be very hard to take in all that technical information. So we're going to take a little brief intermission. Feel free to grab some snacks at the back. Peter's over there, got some snacks. So we'll grab some snacks, then we'll come back in 5 minutes. We'll go through the payload division, and then we'll go through the rest of the presentation. So thank you very much. 5-minute intermission. On Zoom, you guys can do whatever you want, by the way. We don't have snacks delivered, but we'll try our best.
Kevin, can you hear us as well up there?
Yep.
Awesome. I wasn't sure. Thank you.
All righty, I think we're gonna get started again. No rush to take your seats. Feel free, again, at any point in time, just grab some snacks if you forgot something. I know they're very good. But in the meantime, we're gonna start off with the payload division. So you saw the rocket division, and they build obviously all the rocket stuff, but what purpose is a rocket without something to go inside of it? You know, payload, obviously. So in that case, we have the payload division.
Hello, I'm Cameron and I am interim payload lead for HPRC. This year's payload will deploy a quadcopter drone to complete its mission of autonomously locating the rocket using a directional antenna tuned to the frequency of the rocket's telemetry transmission. The payload will be deployed from the rocket once it's falling under parachute and will deploy a quadcopter once safely reaching the ground. Here we can see a general layout of the payload in the rocket. We're housed in the upper airframe with the quadcopter and retention system taking up most of the airframe's length. Since we're deploying from the rocket during descent, we're going to have our own recovery bay and parachute, similar to the one that Rocket already discussed previously. When we deploy from the rocket, we will only take the nose cone and the payload with us, which leaves the upper airframe to descend with the rest of the rocket. So this is the deployment scheme of the payload. After the rocket splits and the upper airframe is ejected from the rocket as seen in phase 2, at around 1,400 feet, the payload's CO2 system is activated, pushing the payload out. This is just after the main parachute deployment, the main parachute deploys on the rocket. So when the payload CO2 system is activated, it pushes the payload out of the upper airframe, allowing the payload to deploy and allowing the payload's parachute to open up and descend. So the payload itself goes through multiple different mechanical configurations in different stages of the mission. In the stowed configuration, the quadcopter and the stabilization legs are folded up inside of the rocket body. once the payload ejects from the rocket body, the payload enters the descent configuration where the stabilization legs unfold and the parachute deploys. When the payload lands and hits the ground, the stabilization legs rotate to make the quadcopter level with the ground, and then the quadcopter arms unfold to allow the quadcopter to take off. We also have a gripper that grips the quadcopter's body so that it doesn't fly out, when it's after it ejects from the rocket. Next, we have our payload mechanical division.
Hello, this is the mechanical portion of the payload, and there's two major systems, the retention system and the quadcopter. So first, the retention system. The payload's retention system is responsible for retaining the quadcopter from ascent to landing, providing a stable platform for the quadcopter, along with deploying its arms and releasing it for flight. The first part of the retention system is the stabilization system. These stabilization pedals deploy when the payload comes out of the upper airframe, and it prevents the payload's bay from rotating mid-flight. And these are deployed using spring power, and as you can see in the video, they come out very well. The second part of the retention system is the aforementioned stabilization, or the rotation part. This mechanism is used to ensure proper deployment of the quadcopter, the sled, and the interior of the payload, and must be rotated once we're on the ground so that the quadcopter is parallel to the ground. To do this, we designed a mechanism powered by a servo that rotates the sled, as you can see in the diagram. And we have a rotating bulkhead with a thrust bearing in between to reduce friction and make it so it slides smoothly as possible. There's a shaft that passes through these two bulkheads and is bolted on either side to make sure that there's no slip in the thrust bearing. And there's a D shaft on the rotating bulkhead so that it can actually rotate. And next is the parachute release mechanism. Once we're on the ground, we don't really want the payload running away from us in high winds. So we have to cut the payload, cut the parachute. To do this, we're using a servo that has a spring counteracting it. The spring is used to ensure that if the servo loses power at any point, the pin stays closed and our payload does not drop from the sky. We used a SolidWorks simulation to make sure that this pin and the pin mounting mechanism has enough strength to keep it from failing under opening load. Once we get to the ground, we're self-righted and we've released the parachute, we have to start deploying the quadcopter. The first step of this is the quad deployment, the arm deployments. We're using a rack and pinion held back by a servo. We're using a rack and pinion because it was an elegant way to keep a low profile and reduce weight. The system is locked with a servo, as you can see in the back, and when we are in visual confirmation and visual sight of the quad, we let the servo know that it's all right to open up, and springs pull the middle rack forward, releasing the arms of the quadcopter, as you'll see later on. The last part, and arguably the most important part of the retention system, is a quadcopter gripper. This quadcopter gripper holds around the quadcopter the whole duration of the flight. And it is uses 4 gears powered by a servo, and it drives the arms outward and inward with gears. Once visual confirmation is made from the payload and the arms are unfolded correctly, we let go of the quadcopters for the quadcopter to finish the mission.
All right. So on to the quadcopter. The quadcopter is a portion of the payload that is responsible for autonomously locating the launch vehicle upon landing. So moving into the structure for the quadcopter, in order to ensure a quadcopter can complete this mission in the largest range of possible wind conditions, we designed an unfolding quadcopter with a large overall frame and propeller size, which also takes up less space and room inside of the rocket when stowed. This design features an H-frame with arms that fold alongside the body and unfold and lock into place once we reach that configuration. The main body of our quadcopter is constructed from a sandwich of carbon fiber plates to provide strength and rigidity to the frame. We also designed a quadcopter arm locking mechanism. To ensure our quadcopter's arms are positively locked into place once unfolded, a spring-actuated pin locking mechanism was designed. This design is a result of iteration on a previous year's design. A shoulder bolt is used as the main structure and motion guide to ensure smooth and precise actuation. Once the arms are unfolded, a spring pushes a 3D printed pin carrier, which has 3 machined aluminum pins, into place. These pins locate into holes in the quadcopter's frame, as well as the quadcopter arms, which prevent them from rotating during flight.
Okay, so moving on to the avionics system of the rocket. The avionics system consists of 4 custom designed PCBs, as well as software to perform critical missions during our flight. Our main requirements were to read and record GPS and sensor data, transmit that data to the ground station, calculate the position and velocity of the rocket, and control the air brake actuation to reach our target apogee. The avionics system is comprised of 4 separate PCBs that are arranged in a stack. We have the controller board, which houses our main processor and handles calculations for the control of the air brakes. The sensor board houses a number of sensors for gathering data on the rocket's position. The telemetry board records the sensor data as well as transmitting it to the ground station. And finally, the power board is tasked with regulating the battery voltage to be used by the other boards. And it also controls the servo and separation charges. All these PCBs were created using Altium Designer, and the system is designed to be modular, so you can easily swap out boards if there's a problem, and it was an easy way to divide up the design work. Some key features of our design include the usage of a teensy microcontroller, which is functioning similar to an Arduino, but is much more powerful than a standard Arduino. The boards are connected with CAN communication protocol, which is resistant to noise and enables us to connect as many boards as we need. The main sensors that we are using include a GPS, an accelerometer, an altimeter, and a temperature sensor. Moving on to the ground station.
So the main purpose of the ground station is to allow the team to be in loop with exactly what's happening with the rocket as it progresses through its flight. To achieve this, we have written custom software to receive and display the telemetry coming from the rocket. The radio that is receiving the data will be connected to a Raspberry Pi microcomputer, which will host its own Wi-Fi network, so the computers running the ground station software can connect and pull data from the rocket. The ground station team has also been simulating, developing, analyzing, and testing custom antennas
suited specifically for long-range and high-altitude communications. On the left is a receiving antenna we have designed, tuned, and simulated using MATLAB, proving effective at our target frequency of 915 megahertz, as seen in the graph of magnitude versus frequency. The higher the magnitude of the gain at a given frequency, the better it is at that frequency. In the Institute Park altimeter test plot, you can see the results of a test we performed across the street in Institute Park, transmitting to the ground station from 580 meters away, as we walked up and down a hill, which was logged by the ground station and later analyzed and put into this plot. Here is the most recent version of the ground station with its full functionality. All relevant information pertaining to the rocket during ascent, descent, and after touchdown can be viewed here and logged to a file on the user's desktop or wherever they specify. What you can see here is a video of the ground station during a test transmission with only the barometer hooked up to the transmitter, which is feeding us temperature and altitude. The graphs update live as telemetry is transmitted from the rocket with a delay from rocket to ground station of approximately 5 milliseconds, with slight variations depending on the range of the rocket.
All right, so I'll be going over the electronics and programming for our payload. So for payload, it's split into two main sections that Keelan and Thierry discussed earlier, which is the retention and the quad. So as you can see, retention is on the left and the quad is on the right. So for the retention software, the system first starts in the passive state, which represents when the rocket's in flight, so including during descent, until landing is detected by the accelerometer. After detecting landing and getting a go-ahead signal from the team, the retention system begins deployment mode, where the quadcopter is oriented to release upwards, the quad arms unfold, and lastly, we do a pre-flight check, which includes checking communications with the ground station, most importantly, making sure that we're receiving the proper sensor data from the drone in order to accurately perform our payload mission. And after everything looks good to go, the quadcopter is released from the retention and flies off. To execute the mission of finding the rocket, the quadcopter takes radio signal readings, which it receives through a radio and antenna on the quadcopter, and it measures the strength of this in order to determine which direction the rocket is in. So the quadcopter will take initial readings in different positions, and based on those, will approximate a direction to fly in. And then as the quad is flying, it will take more data to continuously recalculate the approximate location of the rocket. And so once the quad reaches the rocket, it will verify that it is in the correct position using GPS data. And throughout the flight, the quadcopter will also be sending sensor and location data to the ground station so that the team can track the quadcopter as it's performing its mission. So for the retention electronics, we chose to use the same avionics stack used for the rocket. And this stack includes the sensors necessary to write the quad at the beginning of the quad deployment mode, using specifically a gyroscope and an accelerometer, along with the necessary interfaces for the servos to retain and release the quadcopter. And per competition rules, a big red B GPS will also be included in the system as well to track the retention bay's position during descent and after landing. And lastly, for the quadcopter's electronics, we have the Lux H7 flight controller, which we chose mainly based on cost, size, availability, and ability to interface with other necessary electronics. And the rest of our system includes a camera, a GPS module, motors, ESC, battery, and a custom PCB, which will include a microcontroller to process the signal strength from the antenna and the LoRa radio, and in order to calculate the adjusted heading of the quad.
Awesome. I'd like to invite our guest speaker for tonight, the Provost, Senior Vice President, and future President of Interim President of WPI, Wally. Thank you very much. Cool. Would you like this? Perfect.
So, evening, everyone. I have to say, it's really nice to be with you tonight. I don't know if many of you know this, but so my first job out of school was working for an aerospace company. And so I work for McDonnell Douglas, which is now part of Boeing. And I worked in the corporate research lab. And to be honest with you, I couldn't figure out why they wanted to hire me, which was an interesting thing. So I showed up in St. Louis, Missouri, as a fresh PhD from Cambridge. And they had my television channel program with my name on it. And I'm thinking, you know, this is too much, you know. I'm just fresh out of doing my PhD. And then later when they took me to the airplane plant, I was just amazed by the scale of things, right? So they built missiles, they built commercial and military aircraft. And there was I, you know, this freshly minted PhD. I didn't even have my PhD at the time when they were doing all this fuss. And eventually I figured out that I knew a little bit about some subject they needed, which was how to predict how things and when things fail. And this was really, really important to them, to the point where it determined whether they could have successful helicopters, successful missiles, successful commercial and military planes. And I started to realize the value of an education, you know, because the world out there is very complex, a lot of very amazing things. And during the time that I spent at McDonnell Douglas, I realized the value of theory and practice. Because it's one thing to learn this in college, it's another thing to do this in reality. So a few years ago when I came to WPI, people would often ask me, Wally, why did you come to WPI from Princeton, right? That's a great school. I was in the Department of Mechanical and Aerospace Engineering. And I always tell them that I found in WPI the place that does engineering the way I want to do it. And it's true. It's about theory and practice and a focus on students. And many of you don't realize this, is that you're surrounded by a university in which there's just so much greatness all around us. So today, as we listen to the talks on rocketry, I couldn't help but think about Robert Goddard. So believe it or not, all the ideas that you're pursuing today came from the pioneering work that Robert Goddard did in the deployment of rockets, right? And developing the fuels to make two-stage rocketry possible. And right here at WPI, not very long ago, those experiments that enabled spaceflight to happen the way we know it today were pioneered by Goddard. And he was a tinkerer, but he was also a physicist. But actually, it doesn't matter what he was. He was a WPI student that combined theory and practice and bold imagination. And so imagined a world in which the launching of these rockets would give the critical insights that are needed to enable us to launch vehicles into space. Very bold vision. And without Goddard, we wouldn't be as far as we are today with spaceflight. Now, what's intriguing to me is that you've also kind of demonstrated one thing that I've learned is the most important thing to learn in engineering. And so I come from an engineering family. My father's an engineer, my uncle is an engineer. And I often feel sorry for everybody else in the family, right? Because, you know, when we get together, we start talking. And so one day I asked my dad, who's a Stanford PhD, I said, you know, you've designed all these amazing things. And I'm so impressed. Could you tell me what's the most important lesson that you have about engineering and doing great engineering? And I expected him to say something very complicated. He said, no, it's all about teamwork. I said, what do you mean it's all about teamwork? He says, yes, it's all about teamwork. And he was right. And if you look at what we've just seen today, right, it's been a great example of teamwork, bringing the people who do avionics, mechanical design, bringing the people who do fluid mechanics, and bringing them together to make systems that work, and showing that all these concepts that you learn in the magical classes of WPI are not just theoretical, but you bring them together in creative ways, and you create this rocket that can go 5,000 feet and maybe 10,000 feet. And that's amazing. But here's where it gets better. So with people like Elon Musk, we now have a bold vision that now takes all of that capability and converts it into entrepreneurship, converts it into a vision for space flight and space travel, and all sorts of things that are going to happen in your lifetime and hopefully mine, where you see the magic of what we do at WPI. So for me, I'm truly delighted just to sit back there and watch what you've been doing. I want to use this opportunity to thank all the faculty and staff that are here to support you. I really appreciate this strong support of our students and their daring to dream, and the ways in which you support them, not just academically, but in every way possible to make the WPI experience rich. And I want to thank the club. You know, I'm always excited when I come around and I just see the energy and the creativity that we have in young people, especially. And you might say, well, what's the big deal? Right? What's the big deal? Well, a lot of people are cynical about America, but I'm bullish about America. And I'm bullish about America because I know that the creative spirit of young Americans, the idealism, the vision, the go-getting capabilities that they have will always define the future. And I want to encourage this club to continue to do the work that it's doing, because believe it or not, this is as crucial a part of your formation at WPI as what you get when you go to the classrooms. And so thank you so much for organizing this. I want to thank the companies, the sponsors of this event. Thank you for giving our students the opportunity to really develop the skills to do things that are practical, useful, and inspiring. And I want to thank all of you for inviting me to be part of this. Please, please, if you have any future events or you just need somebody to sit and admire what you do, I'm happy to come here to support you. Thank you.
Thank you very much. That was very touching. I'm gonna add on to that a little bit, try to follow that amazing speech up. I'll try my best. I'm not sure if I can though. With just saying thank you to everyone who's come. Thank you to all the faculty and staff who have helped us get here. Thank you for allowing us to go to test launches, allowing us to go to competition, to all the sponsors that have allowed us to come to their sites and deploy a rocket there, and to the sponsors that have also given us software or funding that have allowed us to get students to competition, to sites, and to build amazing rockets like this. It really couldn't be done without you. And as was said, it's very much a team effort here. I'm one person standing on stage, but I'm representing 126 other students who put their time and effort into this project in its massive complexity. And it really means so much to me as a life experience to stand here today. And I know it means so much to the other students here. So thank you all so very much for coming to this and supporting us throughout this cause. We're going to move a little bit into our sub-team Q&A. Before that, I just want to give you a little bit update. This has obviously been a presentation to demonstrate our capabilities as a team and what we've been able to do thanks to the support that you give us. Of course, we'll be continuing to send out our newsletter and other updates as a team and to how we do at competition. Hopefully, we do pretty well in June. We're on track to succeed, but as our first time in a new competition, it will be all a learning experience. Now, with that said, for the in-person people, we're going to have a bunch of sub-team tables, so to say, where you can go up, you can touch the hardware, you can ask questions about anything that you may have wanted to learn more about during the presentation. And there'll be students there to answer any questions and show you exactly what we've been doing. For those virtually, there's going to be the virtual equivalent of that, where we'll have various breakout rooms, one for each of the 6 sub-teams listed here. We've combined payload mechanical and electronics programming together into the 2 groups there. But you guys can join. That'll be orchestrated by Julia and Jake mainly online. So if you have any questions, please reach out to them. I'll, of course, be up here to answer any questions. I welcome anyone to grab some more food and also just meet and mingle and learn anything else that interests them. Thank you all so much for coming. Have a beautiful night.